Okay, in today's lecture, we're going to start our Chapter 3 material on determinants. And in Section 3.1, we'll give a more formal introduction to determinants. In the last chapter, we were considering the determinant of a 2x2 matrix as a way to determine whether it was invertible or not. And we had a nice simple formula for finding the determinant of a 2x2 matrix. So in this section, in this chapter, we'll consider how to find determinants of larger square matrices and see that these determinants can tell us whether or not a matrix is invertible, and we'll see some other nice properties of determinants throughout the rest of this chapter and the rest of the course. So recall from what we've seen previously, the determinant of a square matrix, so a 2x2, 3x3, or so on, is some scalar associated with that matrix, which will tell us whether the matrix is invertible. So what we've already seen for 2x2 matrices is that they are invertible if and only if the determinant of that matrix is non-zero. And we'll see in this chapter that result holds true in general for any size square matrix. So let's recall some notation. If we're considering a matrix capital A, whose ijth entry is denoted by lowercase a sub ij, we can denote the determinant in one of two standard ways, either det of A, determinant of A, or sometimes we might put parentheses around the A, like it's a function acting on our matrix. Or we could write out the matrix by using each of its entries. So here, since we have a square matrix, our last entry is A sub nn, and then we would use vertical bars around that matrix instead of parentheses or square brackets. It sort of looks like we're taking the absolute value of a matrix, and that's another common notation for finding a determinant. So we'll start by introducing how to find determinants for small square matrices, and then build up to a more general definition for square matrices in general. So the easiest case would be if we have a 1x1 matrix that is essentially just a scalar, some real number, then the determinant of that 1x1 matrix is just the value of that scalar, lowercase a. So as long as the number, or say it's a real number, a, is non-zero, that is, as long as the determinant is non-zero, we have a multiplicative inverse given by 1 over a. And we had seen in our last chapter that if A is a 2x2 matrix, then the determinant of A, which let's say has entries A, B, C, D, would be the product of the entries on the diagonal, A times D, minus the product of the entries on the off diagonal, B times C. So our determinant of this 2x2 would be the product of AD minus BC, and we had seen as long as that value is non-zero, then we can find an inverse for that 2x2 matrix. So a little review with problems that we've already seen. Let's look at some examples where we're working with the determinant of a 2x2 matrix, and we're asked to determine whether our given matrix is singular or non-singular, that is, invertible or not. So in this first example, we have a matrix A, 1, 2, 3, 4, which is a 2x2. So the determinant of this matrix A is found by taking the product of our diagonal entries, 1 times 4, which is 4, minus the product of the off-diagonal entries, 2 and 3, which would be 6. So we're left with a determinant of -2, which is non-zero. So since the determinant is non-zero, we can say that A is non-singular. Or, if we prefer, we can say invertible. That is, an inverse exists. And we could even find the inverse of this 2 by 2 matrix using the formula for the inverse that we saw in Chapter 2. Now in Part B, we have a 2 by 2 matrix B, whose entries are 2, 1, 8, 4. And the determinant of this matrix B would be the product of the diagonal entries, 2 times 4, which is 8, minus the product of the off diagonals, 1 times 8, which is 8. So we're left with a determinant of 0. So we can say here that the matrix B is singular. And so B inverse does not exist. All right. So we now have, what we've known how to find determinants of, say, a 1 by 1 matrix, or just a number, and a 2 by 2 matrix. So let's now try to start extending our definition to larger matrices. So in these next examples, we'll consider 3 by 3 matrices. So if A is a 3 by 3 matrix, the determinant of A, let's say if its entries are denoted as A sub ij, would be found by the following expansion. So I would take the first entry in my first row, that is A11, and then I'm going to multiply by the determinant of a 2 by 2 matrix that we get as a submatrix of the matrix A by deleting the row and the column that A11 lied in. So to explain this in a little more detail, we take that first entry, A11, and then we're going to look at the submatrix that we would get if we were to delete the row and delete the column that A11 lies in. So I'm left with this 2 by 2 submatrix in the bottom right corner, and I would be looking at the determinant of that 2 by 2 submatrix multiplied by that A11 entry. Now from there, let's look at our next term. The next term that we're going to take would be minus A12, so we subtract the second entry in my first row, and then I'm multiplying by the determinant of a 2 by 2 submatrix I get by deleting the row and the column that A12 lie in. So the submatrix that I'm left with here would have entries A21, A23 for the first row, and A31, A33 for the second row. So now moving to our last term, we would take then the sum of A13, the third entry in my first row, times the determinant of the 2 by 2 submatrix we get by deleting the row and the column that A13 lies in. So I would have the matrix A21, A22, A31, A32, and I would take the determinant of that 2 by 2 submatrix. So we're seeing here that we can define the determinant for this 3 by 3 matrix by making use of determinants of 2 by 2 submatrices. And in general, that definition is going to be extended. We'll see how in just a moment. But for now, let's look at an example of finding the determinants of some 3 by 3 matrices. And we're going to use that determinant to identify whether our matrix is singular or non-singular, as we did in the last example. So in this first example, working with a 3 by 3 matrix, the determinant of A would be calculated by taking the first entry in my first row, which was 3, times the determinant of the 2 by 2 submatrix we get by deleting the row and column that 3 lied in. So that would leave me with a submatrix 0, 1, 3, 0. Then our next term, remember we're taking the negative of A1, 2. So taking the negative of this negative 2, we would be adding 2 times the determinant of the 2 by 2 submatrix we get by deleting that row and column. So that would leave me 1, 1, negative 2, 0. And then we add the third entry in our first row, which here is 0. So we have 0, and since this term is 0, well, we don't need to find the determinant of the 2 by 2 submatrix since we're going to multiply it by 0 anyways. But just to write out the details here, if we wanted to consider that last 2 by 2 submatrix, we would have the determinant of 1, 0, negative 2, 3. So let's see what we're left with here. We have 3 times the determinant of this first 2 by 2 submatrix would be the product of the diagonals, so 0, minus the product of the off diagonals, which would be 3. So we have 0 minus 3. Then we were subtracting our negative 2, so we have plus 2 times the determinant of this second 2 by 2 submatrix would be 0 minus a negative 2, so 0 plus 2, and then plus 0 times the determinant of that last matrix would be 0. So simplifying, we have negative 9 plus 4, or negative 5, for the determinant of this matrix A, which is certainly non-zero. So here, the matrix A is non-singular. So we would be able to find an inverse of this matrix A. So let's look at another one. In part B, we would take the determinant of B as 2, the first entry in our first row, times the determinant of the submatrix 1, 2, 3, negative 1. So that submatrix comes again from deleting the first row and first column that entry 2 lied in. Then moving to the next term, remember we're subtracting the second entry in our first row, which was negative 2. And then we multiply by the determinant of the 2 by 2 submatrix we get by deleting our first row and second column of the matrix. So we would have 3, 2, 1, negative 1. And then we add our third term, 3, times the determinant of the 2 by 2 submatrix that we're left with would be 3, 1, 1, 3. So let's see what we have. We had a 2 times a negative 1 minus 6 for the determinant of this first 2 by 2 submatrix. Then minus our negative 2, we have plus 2 times the determinant of the second 2 by 2 would be negative 3 minus 2. And then plus 3 times the determinant of this last submatrix would be 9 minus 1. So let's see what we're left with. We have 2 times negative 7 is negative 14, plus 2 times negative 5 would be negative 10, and then plus 3 times 8 would be 24. So altogether we're left with 0. So we would have a determinant of 0, and so this matrix B is singular or non-invertible. All right. So we've seen here that to find the determinant of a 3 by 3 matrix, we can reduce the calculation or define that determinant to be involving the determinants of smaller 2 by 2 submatrices. and using the entries along the first row of the given matrix times those determinants of the 2x2 submatrices to get our determinant for the larger matrix. So we can extend that definition for larger square matrices. So let's look at a more formal definition of the determinant here. So for n greater than or equal to 2, so we'll be talking about an n by n matrix, let's say A, whose entries are A sub ij. So for a 2x2 or larger square matrix, the determinant is defined as the sum of n terms. So as large as the dimension of our matrix is, we have that many terms that we're going to be adding. And the terms that we're adding are of the form plus or minus A sub 1j, so that is plus or minus the entries in the first row of the matrix, times the determinant of some matrix capital A sub 1j, where the plus and minus signs will be alternating. As we saw in the case of the 3x3 matrix, we had A11 times the determinant of a matrix minus A12 times the determinant, and then plus A13. So our plus minus signs will alternate in general. And these entries, A11, A12, up through A1n, are coming from the first row of our matrix A. Now, we're multiplying those entries times the determinant of some matrix capital A sub 1j. So what is capital A sub 1j? Well, it is the submatrix that is obtained by deleting the first row in the jth column. So whenever I have my A11 entry, I would delete the first row and first column of my matrix and take the determinant of that submatrix. When I have the A12 entry, I would delete the first row but second column, or in general, for A1j, I would delete the first row and jth column. So here, in general, the determinant of a square matrix A would be the sum of these terms, A11 times the determinant of capital A sub 11 minus A12 times the determinant of capital A sub 12, and so on. And in general, our nth term would be negative 1 to the 1 plus n, so that our signs are alternating, plus minus, times A1n times the determinant of the matrix capital A sub 1n, which we could write using sigma notation as follows. So within this expression, or the definition of our determinant, we can identify some particular terms and give them some names. So the term which we're using, or we're taking the determinant of some matrix, say A11, A12, or in general, the determinant of a submatrix, say A sub ij, is denoted as capital M sub ij, and is referred to as the ij minor of the matrix A. Now, those minors that we're taking, the determinant of A sub ij, or M sub ij, is then being multiplied by some term of the form negative 1 to the I plus j power, so that our signs are alternating. And so this alternating sign times the ijth minor is denoted as capital C sub ij, and is referred to as the ij cofactor of the matrix A. So if we look back at our definition for the determinant, another way which we could write that definition is as follows. The determinant of A would be the A11 entry times the 1,1 cofactor of the matrix A, plus the second entry, A12, times the 1,2 cofactor of our matrix A. Now you might ask, well, what? I thought that second term was supposed to be a negative. Well, remember the sign change, this alternating sign, -1 to the I plus j power, is included in that cofactor. So when we have the 1, 2 entry, we would have -1 to the third, so this term will indeed be a negative. And then we keep taking the sum of those terms along our first row times the corresponding cofactor of the matrix. So this formula for the determinant is referred to as a cofactor expansion along the first row of our matrix A. We say here along the first row, since these entries that we're using to multiply by our cofactors were the entries in the first row of our matrix. So in the case that we were working with a 3x3 matrix, let's identify what those minors and cofactors are, get a little more familiar with these terms. So let's say for a 3x3 matrix, let's call it A. Say the same general form that we had seen earlier. So let's say where our ijth entry is little a sub ij. The 1, 1 minor would be the determinant of the 2x2 submatrix we get by deleting the first row, first column. So we would have A22, A23, A32, A33. Now our second minor in that first row cofactor expansion would be M12, which would be the determinant of the submatrix A21, A23, A31, A33. And the 1, 3 minor would be the determinant of A21, A22, A31, A32. That's the submatrix we would get by deleting the first row, third column. And the cofactors, C11, would be the positive value of this 1, 1 minor. C12 would be negative the value of the 1, 2 minor. And C13 would go back to the positive value of the 1, 3 minor. So those cofactor terms are changing sign as we move along the first row. Now, one important theorem involving computing determinants, which will make this process much easier, is the following. It's theorem 3.1 from your textbook, which says that the determinant of a square matrix A can be computed by using a cofactor expansion across any row or down any column. So in the definition that we've introduced in the examples we've been working with, we've been looking at a cofactor expansion along the first row of the matrix A, but this theorem says we can use an expansion along any row or down any column that we wish. And our result would be the same. So for example, a cofactor expansion along the ith row, we could use to calculate the determinant of A as the sum of the entries ai1, ai2, up through ain, times the respective cofactors for those entries. Or if we were interested in a cofactor expansion down the jth column to find the determinant of A, we would take the sum of the entries in that jth column, a1j, a2j, up through anj, times their respective cofactors. And this theorem says that those results will yield the same value for the determinant. So recall here that when we're taking that expansion, the positive or negative sign for the ij cofactor depends on what position A sub ij we are in the matrix. So the factor that we were using in our definition, -1 to the I plus j power, determines a following pattern of signs, which we can see as sort of a checkerboard pattern for the signs along our cofactor expansion. So for the A11 entry, if I and j are both 1, we would have -1 to the second, so we'd have a positive. And if we start moving through our matrix, the signs then change, plus minus, so on. Or if we're going down, say, our first column, we would have plus minus, and so on. So we have that sort of checkerboard pattern for any square matrix. So now that we have this result, let's look at some examples of computing determinants of matrices where maybe the expansion that we're supposed to use is given to us. So in this next example, we have a 3x3 matrix A, and in part A, we are asked to compute the determinant using a cofactor expansion along the first row. So same as what we did in our previous examples. So here, our determinant of A, using a cofactor expansion along the first row, we would have a +1 times the determinant of the submatrix, 1, 1, 4, 2, minus the next entry in our first row, which was 2. So remember, we have to take a negative as we move through our expansion because the signs are changing. Then we are multiplying by the 2x2 submatrix, 3, 1, 2, 2. Then plus we have the third entry in the first row is 4 times the determinant of the submatrix 3, 1, 2, 4. So let's see what we're left with. We have a 1 times the determinant of our first 2x2 is 2 minus 4. Then minus 2 times the determinant of the second submatrix would be 6 minus 2. And then plus 4 times the determinant of our last submatrix is 12 minus 2. So simplifying, we have -2. -2 times 4 would be -8. And then we have a 4 times 10, so plus 40. That leaves us with a determinant of 30. So to illustrate the theorem 3.1 that we just looked at, well, we said we should get the same result if we expand along any other row or column. So to verify that for one particular column, we are asked to compute the determinant of A using a cofactor expansion down the second column of the matrix A. So here, let's look at what we're going to have for our determinant expanding down the second column. So second column of A has a first entry of 2. But if we're using a cofactor expansion down that second column, remember the signs form this checkerboard pattern through our matrix. So the 1, 1 entry corresponds to a positive, so that second entry in the first row would be a negative. So I'm going to take the negative of that second entry times the cofactor for that 1, 2 entry, which would be the determinant of this submatrix 3, 1, 2, 2 with our -1 out in front. And then now moving down my second column, our next entry, we would take a +1 times the determinant of the 2x2 submatrix we get by now deleting this second row, second column. That is the entry that that 1 lied in. So we're left with the matrix 1, 4, 2, 2. And then moving to the last entry in our second column, we have a 4, and we have to take a negative, since our signs were changing as we moved through our matrix, times the 2 by 2 submatrix we get by deleting the row and column that entry lied in. So we're left with a 1, 4, 3, 1. So let's see what we have. We had a negative 2 times 6 minus 2 plus 1 times 2 minus 8, and then negative 4 times 1 minus 12. So we're left with a negative 2 times 4 is negative 8. A 1 times negative 6 is negative 6. And then minus 4 times a negative 11 would give us a positive 44. So 44 minus 14 leaves us with 30. So notice that we do get the same value of the determinant that we found in part A by using a cofactor along the first row or down the second column. So this theorem, 3.1, can be helpful in determining what sort of row or column we should work with to calculate a determinant. In some examples, we'll be trying to find the determinant of some matrix where maybe a particular row or column contains several zeros. So in the case that we have a matrix with a row that consists mostly of 0 entries, we would want to use the cofactor expansion across that row because that cofactor expansion would have many terms that are simply 0. And in that case, the cofactors for those terms in that row don't need to be calculated, since we know we're multiplying by that 0 entry anyways. Or we could use a similar approach, let's say if we were working with a matrix where a particular column had mostly 0 entries. So using that fact, let's look at the following example. So here we are asked to compute the determinant of this 4 by 4 matrix by using a cofactor expansion. And we're told that at each step in this expansion, we want to choose a row or column that involves the least amount of computation. So looking at our matrix here, we see that the second row contains mostly 0 entries. In fact, the only non-zero entry is this 3 term. So let's expand along that second row. I'll make a little note here that we want to expand along row 2. Since most of those entries are 0. So here the determinant of our matrix, let's call that matrix A, would be found by this cofactor expansion. So expanding along that second row, we would have a negative 0, because again, so why negative? Well, our 1, 1 entry has a positive sign. Moving downward from there, we're starting with a negative. So we would have a negative 0 times its cofactor, but we don't care what it is since that entry was 0. Then plus 0 times the cofactor there, but again, we don't care what it is since that entry was 0. And then we move to our 3 entry. So we've got a negative 3 times the cofactor for that 2, 3 entry. So deleting the row that 3 entry lied in and its column, we're left with the determinant of a 3 by 3 matrix: 1, negative 2, 2, 2, negative 4, 5, and 2, 0, 5. And then the last entry in that second row was also 0. So our last term we would be adding along that cofactor expansion is 0, so we're only left with this one term. -3 times the determinant of this 3 by 3 submatrix. So we can see, looking at this new 3 by 3 submatrix, well, let's choose a row or column to use a cofactor expansion along. And I see that for this matrix, I have a single 0 in what I can think of as either the third row or the second column. So I could use a cofactor expansion down the second column or across the third row of this 3 by 3 submatrix to move forward from there. So here I'm going to work with the third row. It doesn't really matter which one you choose. We know by theorem 3.1 we'll end up with the same answer in the end. So we had a -3 times the determinant of this matrix. If we're expanding along our third row, we would have a +2 for that first entry times the cofactor. So we're taking the positive determinant of -2, 2, -4, 5. That is the matrix we get by deleting the first column and third row. Then minus, for that next term, on the third row, we had a 0 value. So we have 0, and we don't care what the cofactor is since we've got that 0 entry. And then moving to the next entry in our third row, we would have a +5 times the determinant of the 2 by 2 submatrix, 1, -2, 2, -4, that we get by deleting that third row, third column. So let's see what we're left with. So I have my -3 out in front. As I distribute, I would have a -3 times 2 is -6 times the determinant of this 2 by 2 submatrix is -10 minus a -8, so +8, minus 0. Then I have my -3 out in front distributing to the +5, so I have -15 times the determinant of this 2 by 2 submatrix on the end would be -4 minus a -4. So I'm left with -6 times -2 is 12, plus this last entry is 0. So I'm left with a determinant of 12. And we see that we were able to find that determinant pretty quickly by using an expansion along the second row of the original matrix, because if I had used the first row, which has all non-zero entries, I would have the sum of 4 different terms, which would all involve computing the determinant of a 3 by 3 submatrix. So we see that starts to get very tedious, but since we did have this one row of mostly zeros, using a cofactor expansion along that row made our work much easier. So let's look at another one. In this next example, we have a similar sort of problem where we are asked to compute the determinant of this 5 by 5 matrix using a cofactor expansion, and along each step we want to choose a row or column that it would involve the least amount of computation. So let's consider how to find the determinant of this matrix A. So I noticed that my fourth row here contains almost all zeros. It only has one non-zero entry. Or similarly, I could use a cofactor expansion down the fifth column, which is all zeros except for one entry. So either approach here wouldn't be too terribly difficult. So let me maybe use an expansion along the fourth row just to illustrate. So here, if I expand along row 4, then the determinant of this matrix would be found by taking that first entry 2, and let's see what sign it has. So from our 1, 1 entry, we have a positive, negative, positive, -2. So we've got a -2 times the determinant of the 4x4 submatrix we get by deleting the row in the column that 2 lied in. So we're left with the determinant of 3, 2, 4, 0, 0, -4, 1, 0, -5, 6, 7, 1, and 2, 3, 2, 0. Now, to find the determinant of this 4x4 submatrix, well, we see that our fourth column contains mostly 0 entries. So let's now expand along that fourth column. So we had our constant -2, and for this expansion, let's look at what sign we have. So we would start with a plus, minus, plus, minus, plus, minus. So we're going to multiply here by that entry -1. And we have, for every other entry in that fourth column, all 0. So we only have that one entry in our cofactor expansion. And we're multiplying by the determinant of the 3x3 submatrix we get by deleting that row and column. So we have 3, 2, 4, 0, -4, 1, and 2, 3, 2. So now, for this last 3x3 submatrix, well, we could use an expansion down the first column since we have a 0 entry only in that first column. And so let's see what we have. So we had our -2 times -1 out in front becomes a +2. And now expanding down the first column of this 3x3 submatrix, we would have a +3 times the determinant of -4, 1, 3, 2, minus that 0 entry, and I don't care what its cofactor is, and then plus 2 times the determinant of 2, 4, -4, 1. All right. So let's see what we're left with. Distributing our 2, we have 6 times the determinant of this first 2x2 is -8 minus 3. And then I have my 2 times 2 becomes 4 times the determinant of this last 2x2 submatrix, which is 2 minus a -16 would be +16. And so let's see what we're left with. We have 6 times a -11, and then plus 4 times 18. So that's -66 plus 72, which leaves us with 6. So here, again, by exploiting the fact that we can expand along any row or column, expanding along a row or column that's mostly zeros makes this problem much easier than trying to expand along, say, the first row, where we would have a bunch of terms involving the determinants of 4x4 submatrices. All right. So let's look at some other examples. In the next examples, we'll consider performing some elementary row operation on a 2x2 matrix. And we're going to see how that row operation would affect the value of the determinant of our matrix. So for the following examples, we want to indicate what row operation is being performed on our matrix and describe its effect on the determinant. So in each of these parts, we're starting with a matrix which is 2x2 of the form A, B, C, D. So recall that the determinant of such a matrix, let me call it A maybe, is A times D minus B times C. So we want to see how a row operation on that matrix would affect the value of the determinant in each case. So in part A, the matrix that we obtain by performing a row operation would be A plus KC B plus KD, and the second row is still just C and D. So we can see here that the row operation which we've performed is that row 1 is replaced by the sum of row 1 plus k times row 2. So we're adding a constant multiple of row 2 to the first row. That was one of our elementary operations. So looking at the determinant of that matrix, A plus KC, B plus KD, and CD for our second row, we have, for the product of our diagonals, A plus KC times D minus the product of the off diagonals, which would be B plus KD times C. So expanding, we have AD plus K times CD minus CB minus K times DC or CD. So we see that this plus or minus KCD term cancel, and we're left with AD minus C times B, or B times C we could write it as. So we see that this is the exact same value as the determinant of A. The determinant did not change here. So by performing that row operation, we get the exact same determinant for our matrix. So let's look at another type of row operation. In part B, we took our original matrix and performed an operation and got the matrix AB, KC, KD. So we can see that comes from the original matrix by multiplying the second row by K. So here the row operation we performed is that we took row 2 and we multiplied it by some scalar K. So let's see what we get for the determinant of that matrix, AB, KC, KD. So here we would have, for the product of our diagonals, A times KD minus product of the off diagonals would be B times KC. So from each of those terms, I could factor out a K, and I'm left with AD minus BC, which is exactly K times the determinant of the original matrix A. So by multiplying row 2 by a constant K, the determinant of the matrix was then K times the determinant of the original. So in our last part, part C, we performed a row operation on our matrix, and the new matrix was CDAB. So we can see that here we've interchanged rows 1 and 2. So we'll start by saying that we've interchanged row 1 and row 2. So let's look at the determinant of this matrix, CDAB. So the product of our diagonals would be C times B minus the product of the off diagonals would be D times A. So this could be thought of as, if we factor out a negative from each term, I would have a positive A times D minus B times C. So this is the negative of the determinant of our original matrix. All right. So we see for our first row operation, adding a scalar multiple of one row to another, there's no change in the determinant. In part B, multiplying a row by a scalar gives us that scalar times the determinant of the original. And for part C, interchanging two rows gave me the negative of the determinant for our original matrix. So we could start to ask the question whether that holds in general. So let's look at an example involving some larger matrices. So in this example, we'll have two 3x3 matrices that are related by some elementary row operation. So we want to determine what row operation was performed and see how it affects our determinant. So our original matrix was the following 3x3. And we can see that to get this second matrix, we multiplied the first row by a constant k. So here, row 1 is multiplied by a constant k. So let's see how that would affect the determinant. So we need to start by looking at the determinant of our first matrix, which was 1, 0, 1, negative 3, 4, negative 4, 2, negative 3, 1. So using a cofactor expansion along the first row, since we have a 0 entry in the first row, we would have a 1 times 4, negative 4, negative 3, 1, plus 0, or minus 0, since we're changing signs as we move through the matrix, plus our 1 times the determinant of negative 3, 4, 2, negative 3. So this gives us a 1 times 4 minus 12 minus 0 plus 1 times 9 minus 8. So we're left with a negative 8 plus 1, or negative 7, for the determinant of our original matrix. Now let's look at the determinant of the matrix we got by multiplying that first row through by k. So we have k, 0, k, negative 3, 4, negative 4, 2, negative 3, 1. So using a cofactor expansion along our first row, we have a positive k times 4, negative 3, 1, minus 0, plus k times the determinant of the matrix negative 3, 4, 2, negative 3. So that gives us k times 4 minus 12 minus 0, plus k times 9 minus 8. So we're left with negative 8 times k plus 1k, which is negative 7 times k. So again, we see that by multiplying that first row of a matrix by a constant k, our determinant is k times the determinant of the original matrix. So you've seen that now for 2x2 and 3x3 matrices. And in this example in particular, you start to realize that that probably holds in general, since using a cofactor expansion along the first row of both matrices yields the same cofactors, our entries are just scaled by the same constant k. So it seems that this would hold true in general. So let's look at another example. So in the following problem, we have a 2x2 matrix A, and we are given some elementary matrix, that is a matrix which performs an elementary operation on a matrix. And we're asked to verify for these matrices that the determinant of the product E times A is equal to the product of the determinants of E and A. All right. So in this example, part A, we have the matrix E, which is the matrix which is formed from the identity by adding k times the first row to the second row. So let's look at the product of E times A. So here, E times A, we have the product of 1, 0, K1 times A, which was A, B, C, D. So for the product of two 2x2 matrices, we get a 2x2, where our first row, first column would be A plus 0, so A. First row, second column would be B plus 0, which is B. Then for our second row, first column, we have K times A plus C. And for our second row, second column, we would have K times B plus D. So taking the determinant of this matrix, E times A, well, for the determinant of a 2x2, we have the product of the diagonals, so A times KB plus D, minus the product of the off diagonals, which would be B times KA plus C. And so we're left with expanding A KB plus AD minus the product of A, K, and B minus the product of B and C. So our plus minus A, K, B cancel, and we're left with AD minus BC. That's the same as the determinant of A. So now we need to find both the determinant of our original matrix A, which was AD minus BC, and the determinant of this elementary matrix E. So looking at that elementary matrix, the product of the diagonals are 1 minus the off diagonals are 0. So we see here that the determinant of the product, E times A, is equal to the product of the determinant of E and the determinant of A. And then the question becomes, well, is the determinant of a product always equal to the product of the determinants? That's a property that we'll look at in our next section. So let's look at the same sort of problem in part B. We have the matrix E, which is 1, 0, 0, K. So that's formed from the identity matrix by multiplying the second row through by K, which corresponds to an elementary row operation. So let's start by finding the product of E times A. That is 1, 0, 0, K times A, B, C, D. So that gives us the matrix A, B, KC, and KD. So for the determinant of that matrix, E times A, we have A times KD minus B times KC, or we can factor out a K, and we're left with AD minus BC. Now the determinant of A is equal to, again, AD minus BC, and the determinant of the elementary matrix E that we had in part B was K minus 0, or just K. So again, we see that the determinant of our product, which was K times AD minus BC, is again equal to the product of the determinants of E and A. All right. So now let's look at another example where we'll multiply a matrix and see how the determinant is affected. So here A is the 2x2 matrix A, B, C, D, and K is a scalar. So we want to find a formula that relates the determinant of K times our matrix to the determinant of the matrix itself. So here, the determinant of the given matrix A is, again, AD minus BC. And let's look at the matrix K times A. So scalar multiplication of a matrix means that we take each entry in our matrix and multiply by that scalar K. So we have the following, and the determinant of this matrix, K times A, is given by the product of the diagonals. So AK times DK gives us A times DK squared, minus the product of the off diagonals, BK and CK, gives us BC times K squared. So we can factor out a K squared from each term, and we're left with AD minus BC, which was the determinant of A. So here for a 2 by 2 matrix, multiplying the matrix through by K gives us a matrix whose determinant is K squared times the determinant of the original. And we'll see a generalization of this in the next section. All right. So in the last part of this section, we'll look at taking the determinant of special types of matrices, which are called either upper or lower triangular. And we'll see that the determinants for these matrices can be calculated very, very quickly. So in this example, we're asked for the determinant of each matrix. So in part A, we have this 2 by 2. So the determinant of A would be given by the product of our diagonals, which is -6, minus the product of the off diagonals, which is 0. So here we have -6, and notice that this matrix, if we think about it being in row echelon form, has zeros everywhere below that main diagonal entry. So when I took the product of those off-diagonal terms, since one of them was 0, I have a 0 value for that product, which means that my determinant was just the product of the entries along that diagonal, that is -2 and +3. Now in part B, we have a 2 by 2 matrix B, which is similar. So our determinant would be the product of the diagonals, which is 14, minus the product of the off diagonals, which is 0. Since in this case, one of those off diagonals was 0, we have the determinant as just the product of the diagonal entries. In this sort of matrix is what is called lower triangular. All of the entries above those main diagonals we saw are 0. So in part C, we now have a 3 by 3 matrix, and we see that for all of the entries below our main diagonal, we have zeros. So that matrix is a 3 by 3 matrix, which is said to be an upper triangular form. And let's look at our determinant by taking a cofactor expansion down the first column, since that seems to have a lot of 0 entries. So for the determinant of C, using a cofactor expansion down the first column, we have a +1 times the determinant of 2503 minus 0 plus 0 as we move down that first column. So we're left with the determinant of C as 1 times the determinant of a 2 by 2 matrix, which is also an upper triangular form. The entries below that diagonal are 0. So we have 1 times the determinant of our 2 by 2 is 6 minus 0. So our determinant is 6. And notice here that that is exactly the product of these diagonal entries. Because we had zeros everywhere else, only those diagonal entries are coming into play. So in part D, we have a 3 by 3 matrix, which is in lower triangular form. All of the entries above the main diagonal are zeros. So using a cofactor expansion, say, along the first row, we would have the determinant of D as 2 times -3, 0, 2, 5, minus 0 plus 0 as we keep moving along the first row. So for the 2 by 2 submatrix that I'm left with, notice that it is also in lower triangular form, since it's got a 0 above the main diagonal. And we find then that our determinant would be 2 times -15 minus 0, so -30, which is, again, we can note the product of these 3 diagonal entries. So what we're seeing in this example is that the determinant of a matrix which is upper triangular or lower triangular seems to be the product of the diagonal entries. And in fact, that holds true in general. So the following theorem, 3.2 from your textbook, says that if A is a triangular matrix, that is upper or lower triangular, then the determinant of A is the product of the entries on the main diagonal. So using that new result, let's look at calculating the determinants of some triangular matrices. So in part A, we have a upper triangular matrix. So its determinant is the product of the diagonals, 1 times 2. In part B, we have a 3 by 3 matrix, which is in upper triangular form. So by theorem 3.2, we know its determinant is the product of the diagonals, 1, -5, and 4, so -20. And in part C, we have a 4 by 4 matrix, which is in lower triangular form, since it has zeros everywhere above that main diagonal. So using theorem 3.2, the determinant is the product of these 4 diagonal entries. So for the first 2, we have -6 times, for the second 2, we had -9, so positive 54 for that determinant. So this theorem allows us to very quickly find the determinants of upper or lower triangular matrices, something that will come into play later in Chapter 5 in our course, and be a very handy technique for calculating these determinants.